2.5 million years ago, on a clear night on the savanna of East Africa, a hominid of the genus Australopithecus looked up at the dark sky. We do not know that this happened, but it probably did, because the species that preceded us were intelligent enough to use tools and navigate landscapes, and the night sky was as much a feature of their world as it is of ours. If one of them looked up on a dark, moonless night toward the constellation we now call Andromeda, their eyes would have detected a faint, elongated smudge of light above the horizon, barely perceptible, present in the peripheral vision before the central gaze. On that night, the photons forming that smudge of light had left the Andromeda Galaxy. They had been traveling at the speed of light ever since, 299,792 kilometers per second, through the intergalactic void, through the empty space between galaxies that contains almost nothing, for 2.5 million years. They were emitted by stars in another galaxy, a collection of approximately 1 trillion suns bound together by gravity into a structure 220,000 light years across, and they were making the longest journey that light can make and still be seen by naked eyes on Earth. Tonight, photons that left the Andromeda Galaxy 2.537 million years ago are arriving at your location. Some of them are entering this room. If you were standing outside in darkness, with fully dark adapted eyes, looking toward the great square of Pegasus, you might see a faint, oval smudge of light about 3 degrees across. That smudge is the Andromeda Galaxy, the most distant object visible to the unaided human eye, and the light composing it has been traveling since before our species existed. Take a slow breath. The Andromeda Galaxy is out there tonight, whether you can see it or not. It is the nearest large galaxy to our own. It is approaching us at approximately 110 kilometers per second, and it contains, distributed across its 220,000 light years of extent, approximately 1 trillion stars. The first written record of the Andromeda Galaxy as an astronomical object was made by the Persian astronomer Abdul-Rahman al-Sufi in his Book of Fixed Stars, completed in 964 AD. Al-Sufi described a little cloud in the region of the sky corresponding to what we now know as M31, noting it as a distinct feature of the sky that had been known to Arab astronomers before him. He is the first person in recorded history to describe what we now know to be an external galaxy. The observation that al-Sufi recorded, and the thousands of years of naked eye observations by unknown observers before him, were of a smudge of light whose true nature was entirely unknown, and would remain unknown for nearly 1,000 years after al-Sufi's catalog was completed. The German astronomer Simon Marius, observing in 1612 with one of the first telescopes applied to the sky, described the nebula in Andromeda as resembling the flame of a candle seen at night through a translucent horn. He was the first person to observe the Andromeda Nebula through a telescope. Charles Messier, the 18th century French comet hunter who compiled his famous catalog of nebulae and clusters specifically to help comet hunters avoid confusing these stationary objects with moving comets, listed the Andromeda Nebula as Object 31 in his catalog in 1764. The designation M31 has been the standard astronomical identifier for the Andromeda Galaxy ever since. The nature of the Andromeda Nebula and of similar spiral nebulae observed in increasing numbers through increasingly powerful telescopes in the 18th and 19th centuries, was the subject of one of the most famous and consequential scientific debates in history. The Great Debate of 1920 was a public debate held at the National Academy of Sciences in Washington, D.C., between two American astronomers, Harlow Shapley and Heber Curtis. Shapley argued that the spiral nebulae were clouds of gas within the Milky Way, which was itself the entire universe. Curtis argued that the spiral nebulae were island universes, entire galaxies external to the Milky Way, and separated from it by enormous distances. The question could not be resolved by the observations available at the time. Both debaters made good arguments, and both made errors. The audience left without a clear victor. The resolution came 3 years later, in October 1923, when Edwin Hubble, working with the 100-inch Hooker telescope on Mount Wilson in California, then the largest telescope in the world, photographed the Andromeda Nebula and identified a Cepheid variable star within it. Cepheid variable stars pulsate in a regular cycle, with a period that is directly related to their intrinsic luminosity, a relationship discovered by Henrietta Leavitt in 1908. By measuring the period of the Cepheid and applying Leavitt's period luminosity relationship, Hubble could determine the star's intrinsic luminosity, and by comparing that with the star's observed brightness, he could calculate its distance. The calculation gave a distance of approximately 300,000 parsecs, or roughly 1,000,000 light-years, though later recalibrations have revised this to 2.537 million light-years. The Andromeda Nebula was at a distance far too great for it to be within the Milky Way. It was an external galaxy, an island universe, and the universe was far larger than anyone had imagined. Hubble wrote var. On the photographic plate he was examining, circling the Cepheid, he had, in that moment, expanded the known universe by a factor of many thousands, established the existence of external galaxies, and provided the foundation for the subsequent discovery that the universe is expanding. Few observations in the history of science have had more immediate and profound consequences. Let your breathing be slow and deep. Hubble's photographic plate is preserved at the Carnegie Observatory's archives. The Cepheid he marked with var is still pulsating, still following the period luminosity relationship that Leavitt discovered, still in the Andromeda Galaxy, still sending its light across 2.537 million light-years to the detectors of telescopes on Earth. The Andromeda Galaxy is a barred spiral galaxy of Hubble type SAB, meaning it has a bar-like structure in its central region and loosely wound spiral arms. It is classified as a giant elliptical spiral, the largest member of the local group of galaxies by mass if we include its dark matter halo, and certainly the largest by visible extent. Its disk spans approximately 220,000 light-years in diameter, approximately twice the diameter of the Milky Way, though some estimates of the Milky Way's outer disk extent suggest the two may be more comparable in size. The distance to M31 is 2.537 million light-years, or approximately 778 kiloparsecs. This distance has been measured by multiple independent methods, Cepheid variable stars. The tip of the red giant branch luminosity eclipsing binary stars and RR Lyrae variable stars, all of which give consistent results. The agreement among these different methods, which depend on different physical assumptions and calibrations, is one of the strongest confirmations of the distance and of the overall accuracy of the extragalactic distance ladder. At a distance of 537 million light-years, the Andromeda Galaxy subtends an angle of about 3 by 1 degrees on the sky, approximately 6 times the diameter of the full moon. This is the angular size of the bright central bulge visible to the naked eye. The full extent of M31's disk, as traced in optical light, extends to about 5 by 1.5 degrees. The even fainter stellar halo, which has been traced in deep photographic surveys, extends to at least 1.3 million light-years from the galaxy's center, or about 3 degrees from the center when seen in the full context of its spatial extent. But this is far too faint for naked eye detection if the full halo of M31 were bright enough to see. It would appear as a disk covering about 100 square degrees of sky, roughly the size of your outstretched fist held at arm's length, and encompassing a large fraction of the Pegasus and Andromeda regions of the sky. The Andromeda Galaxy's central region contains a prominent bulge of old yellow-red stars, similar to the bulge of the Milky Way. Dust lanes, dark ribbons of interstellar material, cross the face of the galaxy and the inner disk, visible as dark asymmetric features in optical images. Beyond the inner disk, the spiral arms wind outward, rich with the blue light of young, hot star-forming regions and the dark clouds of the molecular hydrogen from which new stars are forming. The overall appearance in long-exposure photographs is one of the most beautiful in all of astronomy. A vast, luminous oval of creamy yellow light from the central stellar population, traversed by dark dust lanes, with a faint outer disk fading gradually into the surrounding void. At the very center of the Andromeda Galaxy lies a supermassive black hole designated M31 with a mass of approximately 100 to 140 million solar masses. This is roughly 25 to 35 times the mass of the Milky Way's own central black hole, Sagittarius A, which has a mass of about 4 million solar masses. M31's mass was determined from the velocities of stars orbiting close to the galactic center, following the same methodology used to measure the mass of Sagittarius A. The faster stars orbit close to the center, the more massive the object they are orbiting. The large mass of M31 is consistent with the overall larger size and stellar mass of the Andromeda Galaxy compared to the Milky Way. One of the most surprising discoveries about the Andromeda Galaxy's nucleus was made by the Hubble Space Telescope in 1993. Astronomers expecting a single central concentration of stars found instead that M31's nucleus is double. It appears to contain 2 distinct brightness peaks, designated P1 and P2, separated by about 0.5 parsecs, or about 1.5 light-years. P2 coincides with the position of M31, the supermassive black hole itself. P1 is a concentration of older, cooler stars offset from the black hole. The current explanation for the double nucleus is that P1 consists of stars in an eccentric orbit around the black hole, spending most of their time near the apocenter of their elliptical orbits, the farthest point from the black hole, creating an apparent brightness concentration at the same position as P1. This is analogous to cars on a highway moving more slowly in curves than on straight sections, and therefore appearing more densely concentrated in the curves when viewed from above. The stars of P1 are older and cooler than those of P2, and form a ring-like structure around the black hole that appears double when projected on the sky due to the eccentric orbit geometry. The discovery of the double nucleus of M31 was one of the most interesting results of early Hubble Space Telescope science, and remains one of the most visually striking images of a galactic nucleus obtained by the telescope. The Andromeda Galaxy's stellar halo extends to extraordinary distances. A systematic survey of resolved stars in the outskirts of M31 using the Canada-France-Hawaii Telescope and Hubble Space Telescope has traced the halo to distances of at least 500 kiloparsecs from the center, or about 1.3 million light-years. At these extreme distances, the stellar density is far too low for individual stars to be resolved with most instruments. But the statistics of star counts in deep images reveal the presence of a diffuse population of old metal-poor halo stars extending far beyond the visible disk. The halo of M31 at these outermost extents is already beginning to overlap with the halo of the Milky Way, making the two galaxies, in a sense, already touching at their most diffuse outer boundaries. Embedded in the halo of M31 are numerous stellar streams, elongated structures of stars that trace the remnants of smaller galaxies that have been torn apart and tidally disrupted by the gravitational field of M31 as they fell in and were accreted. The most prominent of these is the giant stellar stream, also called the Andromeda stream, which wraps around the southern halo of M31 as an arc of stars tens of thousands of light years long. The giant stellar stream was discovered in 2001 and is thought to be the remains of a dwarf galaxy that fell into M31 and was disrupted within the past few billion years. Its presence is evidence that the Andromeda Galaxy has a history of cannibalism, of building itself up by accreting smaller satellite galaxies over its lifetime, a process that is common to all large galaxies and that also occurred in the Milky Way's history. The Andromeda Galaxy has a rich system of globular clusters, gravitationally bound spherical collections of old stars that orbit the galaxy at various distances from its center. M31's globular cluster system contains at least 450 confirmed clusters, compared to about 150 for the Milky Way. The most massive globular cluster of M31, Male the 2, also known as G1, is one of the most massive globular clusters in the local group, with a mass of about 10 million solar masses. It is located about 130,000 light-years from M31's center in the outer halo, and is thought by some researchers to be the stripped nucleus of a dwarf galaxy that was tidally disrupted by M31 rather than a simple globular cluster, similar to Omega Centauri in the Milky Way. The Andromeda Galaxy is accompanied by a rich system of satellite galaxies, dwarf galaxies that orbit M31 as the Magellanic Clouds orbit the Milky Way. The most prominent are M32 and M110, both visible in long exposure photographs near M31. M32, also designated NGC 221, is one of the most unusual galaxies in the local group. It is a compact elliptical galaxy, an entire galaxy compressed into a region only about 800 light-years across. M32 is thought to have once been a much larger galaxy that was stripped of its outer stellar population by the tidal forces of M31 as it passed through the larger galaxy's disk, leaving only the dense, compact core behind. The stellar density at M32's center is one of the highest known in any galaxy. In addition to M32 and M110, M31 is known to have at least 30 confirmed satellite dwarf galaxies. And surveys suggest there may be many more below the current detection threshold. These include Andromeda First through XVI and beyond, a sequence of dwarf spheroidal and dwarf irregular galaxies orbiting at distances ranging from a few tens of thousands to a few 100,000 light-years from M31's center. Many of these satellites are very faint, very low surface brightness objects containing only millions to hundreds of millions of stars, the faintest of which were discovered only in the past decade or two using deep photometric surveys. Let your breathing slow and quiet. The Andromeda Galaxy's system of satellites and streams and halo stars is a record of its entire history, preserved in the spatial distribution of stars that extends for over 1 million light-years in every direction from its center. The intact satellites are the survivors, the streams are the dissolved ones, and the diffuse halo of metal poor stars represents the accumulation of billions of years of this process, the ground-down remains of countless minor mergers stirred into a vast, faint cloud that surrounds the galaxy out to distances that human imagination can barely encompass. The local group of galaxies is the collection of gravitationally bound galaxies, of which M31 and the Milky Way are the two dominant members. It contains approximately 80 known galaxies, most of them small dwarf galaxies, distributed over a region roughly 10 million light-years across. The three largest members are M31, the Milky Way, and M33, the Triangulum Galaxy, a smaller spiral galaxy at a distance of about 2.73 million light-years from Earth that is a physical companion to M31. M33 is the third most massive galaxy in the local group and is the most distant object visible to the naked eye under exceptional sky conditions, appearing as a very faint, diffuse patch of light near M31. The local group as a whole is not expanding. The gravitational attraction of its member galaxies is sufficient to overcome the cosmological expansion and keep the group bound together. Beyond the local group, at distances of several million light-years, the nearest other galaxy groups, the M81 group and the Sculptor group, are receding due to cosmological expansion. But within the local group, the gravitational dynamics dominate over the expansion of space, and the member galaxies are in general orbiting and interacting under gravity. M31 is approaching the Milky Way. This was established in the early 20th century when the spectra of M31 were shown to be blue-shifted, meaning M31's light is shifted to shorter wavelengths because the galaxy is approaching us and compressing the light waves by the Doppler effect. Virtually all other galaxies in the universe are redshifted, their light shifted to longer wavelengths because the expansion of space is carrying them away from us. M31 is one of the very few galaxies that is blue-shifted, because its gravitational attraction toward the Milky Way is stronger than the cosmological expansion over the distance between them. The radial velocity of M31 toward the Milky Way is approximately 110 kilometers per second. At this velocity, M31 is covering the 2.537 million light-years between our two galaxies at a rate that will bring the galaxy's centers close together in approximately 4.5 billion years. The collision between M31 and the Milky Way, sometimes called the Andromeda Milky Way collision, And the merged galaxy, sometimes called Milkomeda or Milkdromeda, is one of the most thoroughly studied future events in astrophysics. The word collision is somewhat misleading. The space between individual stars in any galaxy is so vast compared to the sizes of the stars themselves that the actual probability of any two stars colliding during the merger is essentially zero. Even at the densest regions of the merged galaxy, during the most intense phases of the interaction, stars will pass through the region of their partner galaxy like clouds of gnats flying through each other, the gnats almost never actually hitting, because the space between them is so much larger than the gnats themselves. What the collision actually involves is the redistribution of orbital energies through gravitational interactions, the tidal distortion of both galaxies, the triggering of intense starbursts as gas clouds in both galaxies collide and compress, and the eventual settling of both galaxies' stars into a new combined gravitational potential. The merger process will not be instantaneous. Simulations predict that M31 and the Milky Way will first pass through each other in approximately 4.5 billion years, with the passage causing enormous tidal distortions and long streamers of stars pulled out of both galaxies. The two galaxies will then separate, slow, and fall back together for a second pass, then a third, each pass less violent than the last, as orbital energy is dissipated, until after several billion years of this process, the two galaxies merge into a single entity, a large elliptical galaxy containing the combined stellar populations of both progenitors. The entire merger process from first contact to final merger may take 5 to 6 billion years to complete. During the merger, the night sky as seen from any planet that might exist in either galaxy will change dramatically. As M31 approaches in the billions of years before the merger, it will grow larger and brighter in the sky until it fills a significant portion of the night sky, a vast oval of stellar light far brighter than any nebula or the Milky Way itself appears to us today. As the first pass begins, tidal streamers of stars will be visible as luminous arcs stretching across large portions of the sky. Stars will be redistributed into new orbits, and the familiar patterns of the Milky Way band may be disrupted or replaced by new structures. After the final merger, any surviving planetary systems will find themselves in the halo of a new elliptical galaxy, looking out at a sky dramatically different from the one we know. Our sun will survive the merger. It will not be close enough to the gravitational disturbances to be ejected from the galaxy or dramatically changed in its orbit. In 4.5 billion years, the sun will be close to the end of its main sequence life and will be in the early stages of becoming a red giant, a transformation that will make Earth uninhabitable regardless of what the galaxies do. The fate of the solar system in 4.5 billion years is governed more by the sun's own stellar evolution than by the approaching Andromeda Galaxy. The James Webb Space Telescope has observed regions of the Andromeda Galaxy with an angular resolution and infrared sensitivity that reveals individual stars in M31 in ways that were impossible with previous telescopes. JWST's infrared capabilities allow it to see through the dust lanes that obscure optical light, revealing the star-forming regions embedded within the dusty spiral arms of M31 in extraordinary detail. The populations of red giant stars in M31's halo, which are important tracers of the galaxy's formation history and chemical evolution, can be individually resolved and cataloged with JUST, producing the most detailed stellar census of an external galaxy ever achieved. The stellar populations of M31 mirror the dual population known in the Milky Way. The disk of M31 contains population first stars, younger metal-rich stars similar to the Sun, formed within the last few billion years from gas enriched by many generations of previous stellar evolution. The central bulge and the globular clusters contain population 2 stars, older metal-poor stars, formed in the early universe from gas that had experienced less processing by stellar nucleosynthesis. The halo stars, the most distant and diffuse population, are among the most metal-poor stars in the local group, remnants of the earliest phases of galaxy formation when the universe contained almost no elements heavier than helium. The metallicity gradient in M31's disk, the variation in heavy element abundance from the center to the outer disk, has been measured from spectroscopy of M31's planetary nebulae, the glowing shells of gas ejected by dying stars. The gradient shows that the inner disk is more chemically enriched than the outer disk, consistent with the inside-out formation model of galactic disks. The inner regions have been forming stars for longer and have experienced more generations of stellar evolution and enrichment than the outer regions, which still contain pockets of relatively pristine, metal-poor gas. Tonight, let your breathing be the quietest it has been all day. The Andromeda Galaxy is out there in the dark beyond the ceiling above you, 2,537 million light-years away, its trillion stars following their orbits, its central black hole 100 times more massive than ours, its halo of ancient metal-poor stars extending 1 million light-years in every direction, its satellite galaxies orbiting faithfully, its stellar streams recording the history of its past mergers. All of this is happening right now, in the same moment that you are breathing here, in this room, on this small planet, around this ordinary star. The period luminosity relationship that made Hubble's measurement of M31's distance possible was discovered by Henrietta Swan Leavitt, an American astronomer working at the Harvard College Observatory in the early 20th century. Leavitt was employed as a computer, one of a group of women hired to perform the painstaking calculations required to analyze photographic plates of stars. She was assigned to study Cepheid variable stars in the Small Magellanic Cloud, and in 1908, analyzing thousands of photographic plates, she discovered that the brighter Cepheids had longer periods. The more luminous they were, the more slowly they pulsated. Because all the stars in the Small Magellanic Cloud were at roughly the same distance from Earth, the apparent brightness differences between the Cepheids reflected their intrinsic brightness differences, allowing the period luminosity relationship to be established. Leavitt published her discovery in 1908 and expanded it in 1912, noting that the relationship was precise enough to be used as a standard candle for measuring distances. Leavitt never knew that her discovery would become the foundational rung of the cosmic distance ladder that established the scale of the universe. When Hubble applied her period luminosity relationship to the Cepheids he found in the Andromeda Nebula, he transformed her modest observation of stars in the Magellanic Clouds into the measurement that expanded the known universe a millionfold. Leavitt died of cancer in 1921, 2 years before Hubble's discovery was announced. She was posthumously nominated for the Nobel Prize in 1924, but Nobel Prizes are not awarded posthumously, and she did not receive the recognition her work deserved during her lifetime. The crater Leavitt on the Moon is named in her honor. The Hubble Space Telescope Key Project, conducted through the 1990s, used Hubble's ability to resolve individual Cepheid variable stars and galaxies far beyond the local group to calibrate the extragalactic distance scale. By observing Cepheids in 18 galaxies out to a distance of 25 megaparsecs, the project established the Hubble constant at a value of approximately 72 kilometers per second per megaparsec, with an uncertainty of about 10%. This result was one of the primary science justifications for building the Hubble Space Telescope, and its completion was a major milestone in 20th century observational cosmology. The measurement of Cepheid distances in M31 was a critical anchor for this calibration, connecting the nearby Andromeda Galaxy, whose distance had been measured by multiple independent methods, to the more distant galaxies used in the final calibration. Observations of M31 in the radio waveband have revealed the structure of its neutral hydrogen gas, the raw material for star formation. Radio telescopes detect the 21-centimeter emission line of neutral hydrogen produced when the electron in a hydrogen atom flips its spin relative to the proton, releasing a photon with a wavelength of 21 centimeters. Maps of M31 and the 21-centimeter line show a disk of neutral hydrogen extending well beyond the visible stellar disk, with a complex velocity structure reflecting the rotation of the disk. The rotation curve of M31 at large radii, like those of other spiral galaxies, is flat rather than declining, providing some of the earliest and most direct evidence for dark matter in M31's outer halo. The total mass of M31 inferred from its rotation curve, including the dark matter halo necessary to explain the flat rotation curve, is estimated at 1 to 2 trillion solar masses, comparable to or exceeding the total mass of the Milky Way. In the infrared, the Andromeda Galaxy looks dramatically different from its optical appearance. Observations by the Spitzer Space Telescope at wavelengths of 24 micrometers, sensitive to dust heated by young stars, revealed a prominent ring of star formation centered about 10 kiloparsecs from M31's center, a ring of concentrated molecular gas and active star formation that encircles the galaxy's central region. This ring structure, not apparent in optical images where dust obscures the star-forming regions within it, may have been produced by the impact of M32 passing through M31's disk in the past, creating a density wave that propagated outward and triggered the ring of star formation. The WISE satellite observations in the near and mid-infrared revealed the complex structure of M31's spiral arms in unprecedented detail, showing a multi-arm structure that differs significantly from the simple two-arm pattern often depicted in schematic diagrams. The transverse velocity of M31, its velocity across our line of sight rather than toward us, was measured for the first time using the Hubble Space Telescope in 2012. The measurement required tracking the positions of stars in M31 over a period of several years, with a precision of a few micro-arcseconds per year. detecting the tiny proper motion of M31 as a whole against the background of much more distant galaxies. The measured transverse velocity is smaller than the radial velocity, confirming that the collision between M31 and the Milky Way is indeed nearly head-on and will produce a major merger rather than a glancing encounter. The precise orbit of M31 derived from the radial and transverse velocity measurements was used to refine the timing and nature of the collision, placing it at approximately 4.5 billion years from now. The M33 Triangulum Galaxy, the third member of the local group's major galaxies, appears to be in a complex gravitational interaction with M31. Simulations suggest that M33 may have made a close approach to M31 in the past, possibly within the past 3 billion years, and the interaction may have produced some of the tidal features observed in the outskirts of both galaxies. M33 is currently located about 2.73 million light-years from Earth and is very close to M31 in physical space, about 300,000 light-years from M31's center. It is uncertain whether M33 is currently on an orbit that will eventually bring it into the M31 Milky Way merger, or whether it will remain a separate entity orbiting the merged Milky Galaxy. The future of the local group can be described with some confidence. As the universe continues to expand and dark energy drives other galaxy groups beyond the horizon of observability, the local group will become increasingly isolated. The Andromeda Milky Way merger in 4.5 billion years will leave a large elliptical galaxy as the dominant structure of the local group. The smaller satellite galaxies of both progenitors will either be absorbed into the merger product over time or will settle into orbits around the resulting elliptical galaxy. M33 may eventually merge as well, or may remain as a satellite. In the very distant future, hundreds of billions of years from now, the remaining stars of Milky will gradually cool and die, and the galaxy will consist increasingly of white dwarfs, neutron stars, and black holes, cooling in the dark. The sky as seen from a planet in the Andromeda Galaxy tonight would look dramatically different from the sky we see. From M31, the Milky Way would appear as a large spiral galaxy, and the constellation we now call Andromeda's Mirror. Subtending a similar apparent angle on the sky as M31 does to us, a faint, elongated glow of combined starlight. Our sun would be invisible at this distance. It is far too faint to be seen at 2.537 million light-years with the naked eye. From M31, the Milky Way would look as we look at M31, a faint, fuzzy patch of light containing hundreds of billions of stars, none of which can be individually resolved. As M31 approaches the Milky Way over the next 3.9 billion years, it will appear progressively larger and brighter in our sky, assuming any observers remain on Earth or elsewhere in the solar system. In about 1 billion years, M31 may appear as a large oval of diffuse light, noticeably larger than it does today. As the distance has decreased and the apparent angular size has increased, in 2 billion years it will have grown further, beginning to fill a visible region of sky. As the first pass approaches, the tidal distortions will become visible as elongated extensions of light stretching from M31's body, and the Milky Way's own appearance from within will change as tidal forces reshape its disk. During the most intense phases of the merger, any remaining observers would experience a night sky dominated by the colliding and merging structures, with streams and arcs and condensations of stellar light visible across large portions of the sky. After the merger, in a Milky Galaxy, the night sky would lack the band of the Milky Way that we know so well. An elliptical galaxy has no disk structure. Its stars are distributed in a roughly spherical or ellipsoidal swarm with no preferred plane. The night sky from a planet in Milky's halo would show the diffuse glow of the galaxy in all directions rather than concentrated in a single band, and the sky would not have the same clean division between the star-rich Milky Way band and the relatively star-poor polar regions that defines the appearance of our sky. The Andromeda Galaxy is part of the Virgo supercluster, a large-scale structure containing the local group, the Virgo cluster of galaxies, and many other galaxy groups and clusters in a region approximately 110 million light-years across. The Virgo supercluster is itself a component of the Laniakea supercluster, an enormous large-scale structure containing about 100,000 galaxies within a region of approximately 520 million light-years that was defined in 2014 by mapping the peculiar velocity flow field of galaxies, identifying the watershed divide separating galaxies that flow toward the Virgo cluster from those that flow away. The Andromeda Galaxy, as a member of the local group, is gravitationally part of the region that flows toward the center of the Virgo supercluster, the Virgo cluster itself, though the local group is not destined to actually reach the Virgo cluster before the accelerating expansion of the universe makes the journey impossible. In 5 billion years, the Andromeda Galaxy and the Milky Way will begin their merger. Long before then, every human civilization that has existed or will ever exist will be gone. The merger will happen in a universe where no human memory of tonight survives, where no record of the fact that some arrangement of atoms on a planet called Earth once lay in the dark and thought about the Andromeda Galaxy is preserved in any form accessible to anything. The merger will happen in the indifferent grandeur of the cosmos, which does not know that we looked at it. The Andromeda Galaxy's long observational history includes several remarkable moments. In 1888, the English amateur astronomer Isaac Roberts obtained the first successful long-exposure photograph of M31, revealing for the first time its spiral structure. Roberts's photograph, taken with a 20-inch reflector telescope in West Sussex, showed the galaxy as a remarkable object with a bright central nucleus surrounded by a faint spiral pattern unlike any object previously known. Roberts thought he was photographing a forming solar system in the early stages of planetary condensation, because the idea that spiral nebulae were external galaxies was not yet established. His image was in fact a photograph of an entire galaxy containing hundreds of billions of stars, but the scale of the universe was so far from the imagination of 19th century astronomy that this interpretation was not available. In August 1885, a new stellar object appeared in the Andromeda Nebula that became briefly visible to the naked eye, reaching a peak magnitude of about 6.0. Designated S Andromedae, it was initially classified as a nova, a type of stellar explosion known to produce temporary brightening of individual stars. S Andromedae was in fact a supernova, a catastrophic stellar explosion releasing as much energy in a few weeks as the Sun will emit in its entire 10 billion year lifetime. Had the nature and distance of M31 been known at the time, the extraordinary luminosity of S Andromedae, visible to the naked eye in another galaxy at over 1 million light years, would immediately have revealed it as a cataclysm of extraordinary energy. But the distance to M31 was unknown, and the extraordinary luminosity of S Andromedae was one of the data points that later made it difficult to reconcile observations if M31 were a simple nebula within the Milky Way. The American astronomer Vesto Slipher, working at the Lowell Observatory in Arizona, measured the radial velocity of the Andromeda Nebula in 1912 using spectroscopy, detecting the blue shift of M31's spectral lines and deriving a velocity of approach of about 300 kilometers per second. This was the largest velocity ever measured for any astronomical object at the time, far exceeding the velocities of individual stars, and was extremely difficult to explain if M31 were a cloud of gas within the Milky Way. The high velocity was one of the early observational hints that M31 was a much larger and more distant object than a simple gas cloud. In 1952, the German-American astronomer Walter Baade announced at the Rome meeting of the International Astronomical Union that he had discovered a fundamental error in the calibration of Cepheid variable stars that required a complete revision of all extragalactic distances. Working with the 200-inch telescope at Palomar Observatory, Baade had found that there were two distinct types of Cepheid variable stars, population 1 Cepheids in the disk and population 2 Sec Cepheids in the older stellar population, and that the period luminosity relationships for the two populations were different. Hubble's 1923 distance measurement had used population 1 Cepheids and M31, but had applied the calibration derived from population 2 Cepheids and the Milky Way, producing a systematic underestimate of the distance. When Baade applied the correct calibration, the distance to M31 doubled, and the entire extragalactic distance scale was revised upward by a factor of 2. The universe, overnight, became twice as large as it had been. Baade reportedly announced, "The universe is not as small as we thought. The panchromatic Hubble Andromeda Treasury, FAT, is one of the most ambitious observational campaigns in the history of the Hubble Space Telescope." Conducted between 2010 and 2013, FAT used 828 orbits of Hubble Space Telescope time to image approximately 1/3 of M31's disk in 6 photometric bands from ultraviolet to near infrared, resolving approximately 117 million individual stars in M31. The resulting catalog of stars in M31 is the largest catalog of resolved stars in any external galaxy ever produced. The FAT data have been used to study the star formation history of M31's disk in unprecedented detail, mapping where and when different stellar populations formed, and have provided the most comprehensive picture of an external galaxy's stellar content ever assembled. The Galaxy Evolution Explorer, GALEX, observed M31 in ultraviolet light, tracing the distribution of young, hot O and B stars that are the primary emitters of UV radiation. The UV images of M31 show the spiral arms and star-forming ring as bright, knotted structures of recent star formation, contrasting with the smooth, UV-faint central bulge where star formation has largely ceased. The current star formation rate of M31 is estimated at about 0.3 to 0, 5 solar masses per year, significantly lower than the Milky Way's estimated rate of 1 to 3 solar masses per year. M31 is therefore a somewhat more quiescent galaxy than the Milky Way in terms of current star formation activity. The Herschel Space Observatory mapped M31 in far infrared wavelengths from 70 to 500 micrometers, tracing the thermal emission from cold and warm interstellar dust. The Herschel images reveal the complete structure of M31's interstellar medium at wavelengths inaccessible from the ground, showing the cold dust in the molecular cloud complexes where star formation is occurring, the warm dust heated by young stars, and the overall distribution of the gas and dust reservoir that fuels the galaxy's star formation. The combination of GALEX, Spitzer, Herschel, and FAT data has provided the most comprehensive multi-wavelength portrait of any external galaxy ever assembled. The nuclear region of M31 shows no strong evidence for active galactic nucleus activity. M31 is classified as a low-luminosity active galactic nucleus at most, emitting at a level far below what would be expected for a black hole of its mass actively accreting material. This is consistent with M31 being in a relatively quiescent phase of its evolution, with little gas currently being funneled toward the central black hole. By contrast, the much less massive Sagittarius A in the Milky Way shows modest flares of X-ray and infrared activity on daily timescales as small amounts of material fall toward the black hole. The relative quiescence of M31's nucleus, despite its much larger black hole mass, is a reminder that black hole activity depends not just on mass, but on the availability of infalling material. X-ray observations of M31 by the Chandra X-ray Observatory and XME Newton have cataloged hundreds of X-ray sources in the galaxy, including X-ray binaries, where compact objects such as neutron stars or black holes are accreting material from companion stars, supernova remnants glowing in X-rays from the shocked gas produced by stellar explosions, and the diffuse X-ray emission from hot gas and M31's halo. The X-ray binary population of M31 has been used to study the demographics of compact object formation and the history of stellar evolution in the galaxy. The Fermi Gamma Ray Space Telescope has detected extended gamma ray emission from the direction of M31, consistent with the expected signal from the interaction of cosmic rays with interstellar gas in the galaxy. The detection of M31 in gamma rays, announced in 2019, represents the first resolved detection of a normal external galaxy at these very high photon energies, and provides information about the cosmic ray environment in M31 and the overall energy balance of the galaxy. And yet, we did. We looked. We named it. We measured its distance with Cepheid variables and eclipsing binaries and the tip of the red giant branch. We built telescopes to study its nucleus and found a double brightness peak orbiting a black hole 100 million times the mass of the Sun. We traced its halo to 1 million light years. We tracked its satellites. We predicted its future. We built instruments in space to photograph its 117 million individual stars. We detected it in X-rays, in gamma rays, in ultraviolet, in far infrared, in radio waves. This is what the hominid 2.537 million years ago could not do: understand what the smudge of light was. We can. The light that left M31 the night you were born is still out there. 537 million light years into the void and traveling. It will never reach any observer. But the light leaving M31 tonight is arriving at your sky, and if you went outside right now and dark adapted your eyes, you could see it. The photons from M31 that reach your eye do not arrive as a coherent stream from a single source. They arrive from every point in M31's disk and bulge simultaneously, scattered across the roughly 6 by 2 degree area that M31 occupies on the sky. Each photon originated at a different star, at a slightly different distance, so the photons reaching your eye simultaneously actually left M31 at times ranging over hundreds of thousands of years, the time corresponding to the light travel distance across the diameter of the galaxy. When you look at M31, you are seeing a time-averaged picture of the galaxy, the near side as it was 2.46 million years ago, and the far side as it was 2.61 million years ago, the whole image blended into a single impression. The gravitational binding energy of the Andromeda Galaxy, the energy that would be required to pull all of M31's stars completely apart from each other and disperse them to infinite separation, is an almost unimaginably large number. The mass of M31 stars alone, approximately 1 to 2 trillion solar masses, bound together in a volume roughly 220,000 light-years across, represents a gravitational potential energy on the order of 10 to the power of 59 joules. This is roughly 30 orders of magnitude greater than the total energy released by the Sun over its entire 10 billion year main sequence lifetime, and about 10 orders of magnitude greater than the total energy released in a supernova explosion. The gravity of M31 is, in the most literal sense, the force that holds a trillion suns together, and it has been doing so for the past 10 to 12 billion years. The gravitational tidal force of M31 on the Milky Way is already non-zero, even at a distance of 537 million light-years. M31's gravity produces a small differential force across the diameter of the Milky Way, pulling the near side of the Milky Way toward M31 slightly more strongly than the far side. This tidal force is currently far too small to have any measurable effect on the structure or dynamics of the Milky Way, but it will grow enormously as M31 approaches over the next 4 billion years. The tidal deformation of both galaxies as they approach is an inevitable consequence of the inverse square law of gravity. The Andromeda Galaxy was central to one of the most profound revisions in the history of cosmology. Hubble's 1929 discovery that distant galaxies are receding from us with recession velocities proportional to their distances established the expanding universe that is now the foundation of modern cosmology. The distances Hubble used to establish this relationship were all measured using Cepheid variable stars in nearby galaxies, calibrated against the distances he had measured in M31 in 1923. Without the accurate distance to M31 provided by the Cepheids Hubble found in 1923, the extragalactic distance scale that enabled the discovery of the expanding universe would not have been possible. M31 does not recede with the Hubble expansion. It is gravitationally bound to the Milky Way and approaching at 110 kilometers per second. But by establishing the distance scale that revealed the expansion of the universe in all other directions, M31 paradoxically became the key to discovering the largest scale phenomenon in the cosmos. The nearest galaxy, the one approaching us, was the calibration standard that revealed that all other galaxies are flying apart. Let the weight of that settle around you. The Andromeda Galaxy, faint smudge in the autumn sky, has anchored every distance measurement in the observable universe. It has been the reference point from which astronomers triangulated the scale of everything, and it is approaching 110 kilometers per second every second, all night to night, while you sleep. Rest now. The Andromeda Galaxy is doing what it has been doing for the past 10 billion years, shining quietly in the void, its trillion stars following their orbits, its ancient light flowing outward in every direction through the intergalactic dark. Some small fraction of it arriving at a small planet where tonight you are breathing slowly in the quiet, drifting toward sleep. In 4.5 billion years it will be here, but tonight it is 2.537 million light years away, and you are exactly where you are, and the light is traveling, and you are breathing, and there is nothing else required of you at all. The universe contains approximately 2 trillion galaxies. Of those 2 trillion, only one is visible to your naked eye from your current latitude on a clear autumn night. Only one has approached close enough over the 13.8 billion years of cosmic history to be seen without any instrument at all by the unenhanced human eye. That one galaxy out of 2 trillion is the Andromeda Galaxy. The light from it is arriving at your retina right now, even through walls and clouds and distance. The 2.537 million-year-old photons diffusing through the atmosphere and your ceiling and the air of your room, carrying the faintest trace of 1 trillion suns to the place where you are lying. Good night. The Andromeda Galaxy is out there. It always will be.